So right here, we do have office hours posted. I forgot to mention this in the last lecture. We do have office hours. My office hours are Thursday, 1 to 2. So tomorrow, 1 to 2, stop by my office. I'll be there ready to answer your questions. I also have office hours Tuesdays, 1 to 3. You can try to stop by during these office hours, but these are shared with 116. I have 387, I think was the final count, 116 students. As soon as that course starts ramping up, those students are going to flood those 2 hours. So it'll be tougher to get your questions answered. You have to wait in line, things like that. The Thursday office hour, that's CSE 312 only. There won't be crowds, there won't be lines, unless they're lines with your classmates in this class. 312 only. So I wanted that one office hour to give y'all an opportunity to be able to come see me. So we have that 312 only office hour. Our TA, Nick Schaefer, he has office hours right after class on Mondays and Wednesdays. Just double check, make sure I got that right. Mondays and Wednesdays, he'll be in the TA area outside of Davis 302. I assume you're all familiar with that by now. Just in case, third floor of Davis, if you're facing towards the elevators, turn to the left and walk to the end of that hall, that common area. That's where you can find Nick. That's where he'll be. We're going to feel out the office hours. My schedule is pretty packed as it is, but Nick does have some room in his schedule. He can potentially add some more office hours. So if those hours do get crowded, Nick will let me know. If just to add some redundancy, let me know as well. If you start seeing lines and you can't see Nick, he can expand his hours. I just don't want to expand them and have hours that aren't used. Also, if you can't make any of our hours, that'd be a good reason for Nick to add some more hours as well. If you can't make any of those hours, let us know what hours you can make, and maybe Nick can add an hour that fits into your schedule. So right after class today, Nick will be waiting for your questions. Tomorrow at 1, I'll be waiting for your questions, etc. Okay, so last time we talked about the physical internet and the internet protocol, and we learned that that really is what the internet is. The internet is cables physically connecting different locations, routers connecting those cables, and then this internet protocol with primarily the IP address. Every device connected to one of these networks, connected with these cables or with Wi-Fi, has an IP address. And the IP address determines how a router is going to get a packet, get information on the internet to its destination, to the proper destination. These routers work to maximize speed. They are very simple devices, very simple programming. The actual routing, how they figure out how to route through the internet, that gets very complicated. But once it knows what the next hop of a packet is, it's very quick to look up the destination IP address and just send it to that next hop. There is no fault tolerance in the internet. The internet is an unreliable network. You have no guarantee that your packets are going to make it to its destination. And also the packets have a maximum size. You can only send so much information at once over the internet. These routers are designed to have use a lot of small packets and be able to forward those packets quickly. So, how do we use the internet if it's unreliable and can't handle large amounts of data? These are two seemingly very large drawbacks, but we still use the internet every day. We can download large files. We know we get around those restrictions. So how do we do that? And of course, not pulling any punches here, it's TCP. So TCP is going to come in and save the day and make the internet more usable. So the internet doesn't care about TCP. This is something that we use on our end. Our software has to implement TCP. That's why the first thing you write in your software is the TCP socket server. TCP is used on the internet, but the internet never cares that TCP is being used on it. There's nothing in the actual internet itself that really cares about TCP or knows about TCP. It's a protocol that we use on the endpoints to enable this communication. So the big thing we want to solve is this fault, this unreliability, and also large files. So let's see how TCP does each one of those. So first, we're going to connect to another machine. In IP, the only thing that IP defines is this way of routing packets through the internet. TCP says, okay, let's make this a little more sophisticated, let's make this a little more official, and let's make an actual connection between two devices on the internet. So to make that connection, to be able to have a more persistent connection between two machines, TCP is going to start with this three-way handshake. The client, the browser for our cases, for our purposes, is going to send some sync message to the server to initiate the TCP. And this is going to be a message that just contains a random number. We're going to call it M in this, for TCP. The server is going to get that sync message, and it's going to return to the client with an acknowledgement, which is the number that the client sent plus 1. So M is just a random number. It's different every time you initiate a TCP connection, and the server is going to respond with that number plus 1. Now, this seems like a silly thing to do. We're just adding 1 to a number, big deal. But this actually gives us a lot of information with that plus 1. What this tells the client is that the server, 1, exists and can send things back to it, and 2, is speaking the same encodings, the same protocols. It can actually read the message, parse through, figure out how, where M is in the message, how it's encoded. It just confirms that we're both speaking TCP. So plus 1 is just some arbitrary, simple operation, but it gives us confidence that we can communicate effectively because they were able to read M and modify it. Server would like that same acknowledgement, so it's going to send its own random number n, and the client's going to respond with n plus 1 to verify that it can speak TCP, it can parse through the message, it knows what it's looking for. Just confirms that we both know TCP and that it's programmed correctly on both ends. This last ACK is usually contains the first request. If this is a request for index.html, for example, this last ACK from the client is usually going to contain that request as well. So the server can start processing that. No need to waste that extra communication, have another round trip here. So once we have a connection, now we can send multiple packets between each other with that one single connection. Whereas before, with just IP, we can just send one packet. Each packet is completely independent of each other. TCP with this connection is going to give us a way to have more communication, more two-way communication with this connection. So, whenever let me back up just 1 second, or jump ahead, I guess. So, if we have a dropped packet, if the client or the server sends a packet to the server, it's too early for this sometimes. If the server sends a packet to the client and the client doesn't receive that packet, with that persistent connection, we can get some feedback from the client. The client can say, hey, I never got that packet that you sent me. Can you resend that packet? And this is a big way that we get reliability over TCP. The client can ask to resend a message, which we couldn't necessarily do with just IP without doing something like this on top of it. So we have this connection. Client sends a request. It's going to wait some specified amount of time, some timeout. If that request times out, it's going to say, hey, server, if you did send that to me, can you send that to me again? I didn't get the response from you. Now, when the response is too large for a single packet, here's the other thing we have to solve. What TCP is going to do is chop up that request into however many packets it takes to be able to send that entire file. So say I have a 4 gigabyte file, some big movie that I want to download. TCP is going to chop that into tons of different parts, distribute it across many packets, and then send all of those packets to the client. Before that happens, the server is going to send some metadata. It's going to say, hey, I'm about to send you 3,000 packets, or whatever the case may be, however many packets it might be. I'm going to send you this many packets to serve your request. So heads up, this is how many you should expect and you're going to get this many packets. And it just sends all those packets at once, and these packets can arrive out of order. When we get these packets in our browser, they can be in any order. Maybe maybe a router updated its forwarding table mid-transmission during this. Maybe a router was down, and a lot of things can happen. We can get these out of order. So each packet has a sequence number. So once all the packets are downloaded, once we get all the packets over the internet, our client, TCP client, is going to sort all the packets by sequence number and then piece them all together to get the larger request. So this is how we can get these large files that are larger than one packet over the internet. We can send all the packets and then reassemble them on the other end. Any question?
What if the client doesn't get the metadata?
So the client doesn't get the metadata, I don't know off the top of my head exactly what they do, but I would assume there would be a timeout on that first request if they don't get the metadata, and it times out, the client would resend that request. Yeah, because if they don't have the metadata, they're kind of, it's a non-starter. So they have to get that first. And if any packet is dropped, if we have any dropped packets in this whole file, what we would not want to do is say, hey, I missed one packet, I missed a few kbytes in that file. Hey server, can you send me all three, did I say 3 earlier? Send me all 3 gigabytes of that file again. We don't want to do that, and we don't have to do that with TCP. We're just going to get all the sequence numbers, again, wait some specified timeout. If it's been too long, we're going to say, hey server, I'm missing packet number 534. Send me that packet again, because it looks like something happened there. So it's going to send that one packet, and then we can reassemble the content, whatever we're downloading after that, once we get any packets that were lost. So we have now reliability and large files by using TCP, mostly by having some connection, some metadata communication, so that we can know and detect if we missed a missed a packet, and then request resends. Hey, resend me that packet, because I didn't get it.
Is there any kind of integrity check on packets? Checksums?
I believe there is a checksum on the packets. On the TCP, I'm digging through all my knowledge. There is a checksum at some point here. I don't know if it's in IP or TCP, to be honest. I think it might even be in IP, question mark. I'm not 100% in that. And I believe, I'm really digging here, so don't take my word for this one, but I believe there are checksums built into one of these protocols, but they started ignoring them because it was using up too much processing power in the routers for something that was almost always fine. And I don't know, I'm just guessing here. I'm trying to remember years and years back. And anyway, the concept of a port number is also something that comes from TCP. You're talking about port numbers as a TCP thing. So for example, if I want to have many TCP connections simultaneously, which we all do all the time, if you have 2 tabs open in a browser, you have to have 2 TCP connections to be able to support both those tabs. To distinguish this, we use port numbers and say, let's not just send something to a specific IP address, because if you have 2 tabs open and your network card gets a packet for a specific IP address for your IP address, how does it know which tab to send that packet to? We need some way of identifying that to be able to specify that. So TCP introduces these port numbers and says, okay, give each tab a different port number, and then I'm going to send not just a packet, not just to an IP address, but a specific port number on that IP address. And ports, there's nothing magical here. It's just a number. We just come up with a number and say this is for this port number. And then on our side, we have software that says, okay, I'm going to look for this port number and then send it where it has to go for that port. Not magical here, it's just a number. And servers have some common port numbers. For example, HTTP. If you have an HTTP server, it's usually going to run on port 80. For our assignments, we usually use 8000 or 8080, which are development port numbers. If we're just developing and we're not going live out to production on the internet, we usually use those higher numbers just for development purposes. And then if we're encrypted, we would use port 443. Talk more about things like that. That'll be more relevant later in the semester. But those port numbers are part of the TCP protocol, not the IP protocol. This port number IP combination, once we talk at that level, we're talking about the yield TCP IP. So TCP IP, they're usually used in conjunction. So you usually hear them just talk about together TCP IP, but they are two completely separate protocols that combine to be able to make the internet a reliable and usable network. We'll talk about that at length. If you are interested more about TCP and IP and those questions that I'm not able to answer, if you want to have those answered in great depth, we have a wonderful course, CSE 489, Modern Networking Concepts. I would recommend this course. It's going to talk about TCP, IP, UDP, which we won't talk about at all in this course, and how the routing tables of the routers of the internet are updated. How do we optimize for speed and somewhat reliability over the internet? How do we detect if a router went down? All these timeouts, how do those work? The checksums, they'll be able to answer that question. That'll be a topic in that class. All kinds of good information. For this class, we just assume that TCP IP works. I'm not even asking you to implement this, not asking you to do any TCP IP. We just pull in libraries to do this for us. I just want to give some background on these slides to show you what are we actually getting when we import that library. But if you want to know in detail, everything TCP and down, in the network stack, I didn't introduce the network stack, I guess. TCP, IP, a little bit of the physical layer, that's more electrical engineering's domain. But if you're interested in those topics, that's your course. We're going to take TCP and IP for granted and build on top of these protocols. So above TCP, that's what we're going to work with, starting with HTTP, as we'll talk about throughout the next couple of weeks. So that's the separation between these courses. If you do want to know when you say, hey library, give me a TCP socket server, what's going on there, that's your course. That's the one you want to take. So let's do a quick demo. I'll do a demo in Scala of starting a TCP socket server. And I'll try to focus on, most of you won't be using Scala, I would assume. So I'll try to focus on the concepts and what needs to be done with whatever library or whatever language you choose to use. So let's see some Scala. So here's my full code to start a TCP socket server. We're using libraries here, so you should expect it to not be a ton of code for any language. I mean, some languages, some libraries will be more or less, but you shouldn't have a whole lot of code. So whatever language you're using, you're going to have, at some point, you're going to have to specify, localhost might be assumed in a lot of libraries, you're going to have to specify the port number. What port number do you want to listen to? So whenever your network card gets a request, gets a TCP packet for a specific port number, if it matches your number here, it's going to send it to your program. Now you can only have one process on your machine listening on a specific port number at a single time. This is why we usually use these development port numbers. Something's probably already using port 80 on our machines. If I try to use 80 here, something's going to be using that port already. Which I have something running. I don't know exactly what I'm running on port 80, but something keeps blocking it. Anyway, so I'm going to choose port 8000. 8000 and 8080 are the common development ones. There's no magic to those, no real meaning. That's just kind of the standard that people chose. Let's use those for our development ports when we're developing web apps.
Well, this code won't be posted, will it?
Not really, but the video will exist. You can always look at it. You might be able to. Yeah, it'll be in the video. I'll stick with that. So here I want to. I'm going to bind. I'm going to ask my library to bind this. My IP address, localhost, is just whatever my IP address, the IP address of this machine, and saying, let's use this IP address. And the port number, I'm going to bind that, and this is going to happen in any language, any library. This is where we're asking the operating system, hey, I want this port number to be forwarded to me. I want this port number. And your OS is going to do one of two things. It's either going to say, cool, here's your port. Anytime I get a packet, or every time I get some network traffic on this port, I'm going to send it to you. Or it's going to say, port already in use. Some process is already listening on that port number, so you can't have it. It's not, you can't have it, you can't use it, and we're going to get an error, and our program's going to crash. This is going to be actually pretty common to have a port already in use, because when you're developing, you're probably going to be using that port. And if you just refresh, so if I run this server and just rerun the code, if I'm running this, everything's going to be fine. Actually, I don't think this library does it. I think this library frees up the port gracefully. If I refresh this, let's see if we get it to crash. Oh, yeah, I think this library works too gracefully. But if you, in certain languages, in C, I always have this behavior. If you don't give that port explicitly back to the operating system, if you don't say, hey, I'm done with this port, it's still going to assume that you need that port until it does its cleanup. It might see the process is killed or whatever, and then it's going to free up that port. But that can take some time, so you might be the one using that port and blocking yourself. So if you're getting frustrated, you keep getting port in use, it might be you that's using it. The quick solution to that is just change your port number. Use a different port, and then that'll give you time to free up that other port. You can switch between ports or just keep incrementing by one each time you get that. So just a heads up, depends on your language and library, but you might get that error. I've seen tons of those error messages in my day. Or you can make sure that your port is, that your connection, that your server is closing gracefully and releasing that port back to the OS, which will be different in each language and library. So you have to ask your operating system, hey, I want this port number. You'll have some way, this is less important, but in a little different in each language. But I like to print some message just to say, hey, I'm listening on this port. We got this port set up. So the way Scala works is I'm going to send this bind message to my operating system concurrently, and then everything else is based on messages, based on an event-based architecture. So when certain events happen, in this case messages received, we're going to react differently. So when we send this bind message, we're going to get, if everything's successful, a bound response. And when I get that bound response, confirming that, hey, we got that port, everything's cool, I want to just print a little message to myself, just a little thing in the console to say, we're listening on port 8000. If you've used web frameworks before, most frameworks have some message like this. They're going to say, hey, you're up and running on this port number, everything seems to be going fine. So I like that message too. I want to recreate that. It's optional, but helpful. If you're trying to debug something and you don't have this message and you realize, oh, my server was never ever running, that can be a really frustrating one and a silly error to have. And then once I have a connection, so I get a client connecting, they're initiating a three-way handshake and they want to connect to me. I'm going to print that too. I just want to say who's connecting to me. And for this library, I have to send back a register message. I have to say, hey, okay, you're wanting to connect. Let's finish this handshake. Let's do this connection. Let's do this thing and make this official. So you send this message to complete the connection. Whenever somebody closes, if the client closes their side of the connection, I'm going to get this peer closed message, and I'm just going to do something whenever that happens. I'm just printing a message to the screen. And the big one, whenever I get information over this connection, give me that information so I can process it. This is the one where we're going to spend most of our time when we're working with HTTP. When I receive a message, at this point, TCP has already done the sequence numbers, has already requested resends for drop packets if necessary, if applicable. It already reassembled the information. It already did all of that, and it's giving me one message, one final received message over the network. So at this point, we don't have to worry about TCP, IP. All of that's going to be done for us in the library, and we get one reliable message. When a browser is sending us a message, we can assume that that's just going to get there because that's what TCP gives us. And when we send a message back, we can assume that that's going to get there to the browser because that's what TCP gives us. So all that TCP IP stuff, it's all done in this code. It's all done by the library, and we don't have to worry about that. Now, anything beyond that, no libraries, we have to parse our own HTTP and stuff like that. But to get to this point, to get the messages and send the messages, we're not sending messages today, we'll do that Friday. But to get to this point, libraries go nuts. So let's run this. Well, it's already running. So we're running on port 8000. And if I go to my browser, so we could write a TCP client as well. We could write a client that's going to send messages, send TCP messages, and use the internet, use this TCP IP, these network protocols, and just send direct messages and then reply with messages. But we don't have to in this course. We already have our browsers, which will be our TCP clients. If you want to just play around with TCP, or if the tutorial you're going through to do TCP in your language, if they have TCP client code, feel free to play with it. It's interesting stuff. For our purposes, the browser is going to be our TCP client. So if I go to localhost, so my URL is going to be the IP and then the port number separated by a colon. If I go to localhost, it's a little small, I know, but localhost colon 8000, that's where my server is running. If I go here, I'm of course going to get nothing because we haven't implemented anything yet. So I don't get anything in my browser, but what did happen, if I go to my code, is I can see what the browser sent me. I'm printing that message, I'm receiving that message, and I'm printing it to the screen, and I can see the HTTP request that I received from that browser. So that browser just sent this HTTP request to my server, and now I can start working with this request. I can parse this, I can figure out what to send back to the browser, to the client at this point. And that's what we'll spend tons and tons of time on. Yes?
So did you pick the port number, or did he give it?
No, good question. So I did not pick I picked the port number 8000 for my server, but with your browser, each time you make open a new browser window, a new browser tab, you're going to get some randomish high port number. So these port numbers, I believe I have another tab. Maybe I don't. I might in another one of my browser windows. But I think I have another tab open. That's what the second one is for. But I have two clients connecting to my server, and they get random port numbers. So the web servers on the internet, they're using ports 80, 440, or 443. But your browser does not use those port numbers. Your browser is going to use whatever random port number it got. So this is how we can have multiple tabs, because we're getting these random large port numbers, which we have many of. We can as many numbers as can fit in 16-bit. I shouldn't even guess 16-bit value. I think. We have a lot of different numbers. We have a lot of different tabs. At some point, we would actually run out of port numbers. We had a ridiculous number of tabs. But we're going to get these random port numbers. So now when my server says, okay, I need to send back to this client, I'm going to send back to localhost. Excuse me, this is a special IP address reserved for localhost, and I'm going to send it to this port number. My network card gets that, and it says, oh, that port number is for this process, sends it to that tab in that browser, and then that tab in that browser can handle that response however it needs to. So this is how we say which tab in which window these TCP messages are going to get sent to. So that's how we route everything. If all the tabs were listening on port 80, and 2 of them are sending HTTP requests to different servers at the same time, and we get both responses, how do we know where that goes? This is the answer to that. Each tab gets its own port number.
Is there a way to ask the operating system for an open port, or do you just have to?
As far as I know, you have to just ask. No, you have good questions. As far as I know, you just have to ask for a port number. I don't know if you can just ask for an open port number. I believe you just have a loop that says ask for a port number. If that port's not available, increment, which I would guess is what the browser is doing here. If say if Opera and Chrome are starting at the same number and then incrementing by 1, they would just ask for each port number and then get it back. I don't believe there's a way to say, give me an open port. There may be, but that'd be a good question in operating systems. I'll advertise another class today. Our operating systems class would definitely have the answer for you there. For asking the operating system for an open port.
Oh.
If there's a method that's standard across all operating systems that says, this is how you ask me for any open port, and if you don't care about the number, operating systems, that class would have an answer for you. What do we do with it? So what is that information? What is HTTP? This is where we're going to spend at least the next 3 weeks. Just talking about this protocol. Everything so far has been either background or just messing around in the front end a little bit like we did last week. So HTTP. Network error. Give me 1 sec here. Why are you doing this? Huh. Okay. Everything's fine, nothing's screwed. So, quick roadmap, what we talked about. Physical internet, the world's wrapped in cables. IP, how do we route messages through these cables to get to its proper destination in an unreliable, best effort basis, best effort kind of way, and then TCP to make this connection reliable. So now we have a stable, reliable way to use the internet. What are we going to do with it? Well, anything that our hearts desire. And we're going to use HTTP for that. So when we send a packet over the internet, it's a very simplified view. Again, modern networking concepts will dive into much more depth on the packet structure and the network stack. Those are topics we won't really talk about in this class, just in passing like this. But when we send a packet over the internet, we're going to have our IP headers. That's what the routers of the internet are going to read. And the routers of the internet don't care what's in here. But once our network card gets this packet, it's going to peel back the IP headers and then read the TCP headers to figure out where this packet is going to go. This is going to say, okay, what port number, where do I send this, what sequence number, and things like that. Once those TCP headers are read, we're getting down to the HTTP once everything's reassembled and all these packets all the sequence numbers are read and everything. Once that's all reassembled, the first thing in that reassembled packet is going to be the HTTP headers, and that's what we want to read to be able to figure out how our programs are going to handle this request. And then, optionally, we can have some content in the actual HTTP requests as well. So by the time we get a packet, or reassembled packets, we're going to be looking at the HTTP headers. These headers are already going to be peeled off. Other software already read them, handled them how they need to handle them, and then remove those headers. So we never access those headers. We don't have to worry about those HTTP headers we do. We will use TCP exclusively if you're hoping to see UDP. It's not happening in this class. There are very few use cases for UDP, and I'm quite sure that you can't even use UDP in a browser. There's only certain types of apps, and they have to be homegrown desktop apps. You can't run them in a browser that are going to use UDP. So if you know what that is, don't get your hopes up if you're hoping for it. Bless you. It's mostly used for video conferencing. So UDP is an unreliable protocol. It's a counterpart to TCP. It's really only used for video conferencing when you can tolerate dropped packets, but you need speed. Like if you have a dropped packet when you're on like a Skype call with somebody, you really don't care that much about that dropped packet. You don't want to go back in time and watch that packet again, but you do want to be live, or at least as live as possible. You want minimal delay, you want minimal latency. That's where an unreliable protocol like UDP comes in. For almost every other purpose, TCP, you want that reliable connection. Even if you're streaming video, even if you're streaming live video online, you usually don't care about that delay. If you're watching Twitch, you don't really care about a few seconds delay. In most cases, that's not going to affect your experience at all. So we use TCP and I have this reliable connection to send those videos, even streaming video. But when you have two-way communication like a video call, that's one case where you would actually want UDP. I want to skip ahead a little bit. So let's talk about the web server. We want software, what we're going to write in this class is software that speaks HTTP. So we want our code that's running a TCP socket server to get these HTTP requests and be able to communicate with the browser with this protocol. And we're going to do this with requests and responses. So our software is going to get an HTTP request, which we saw one in the console already. Our browser is going to send these HTTP requests, and we want to respond with HTTP responses. This is the fundamental kind of loop of HTTP. It's a request-response protocol. It's all completely based on these requests and responses. And a little bit of terminology here. I'll talk about it on the next slide. But we have front-end and back-end. You probably heard this before. I've said it in this class already. But let's take one step back to talk about what exactly we mean by this. The front end is any part of a web app that runs in the browser. This is all the HTTP, the CSS, and the JavaScript. That's all front end. Those are front end technologies. Any front end frameworks, that's all running in the browser. The back end is anything running on the server side that's on the other side of the internet. The server side, or back end code, this is where we'll start shifting our focus as we work on these, on HTTP. We're working on the back end. This is anything that the client doesn't have access to. It doesn't have direct access. The only way the client can interact with the back end is by sending HTTP requests. So the client can say, hey, back end, give me your HTML. Okay, I'll send the HTML. Parse through that HTML and look for each link, anything that's referenced in that HTML, and then send requests for the rest of the content, and then the server can send the rest of the content. But the client can't just go to the back end and grab that HTML. They have to communicate through these HTTP requests. So if there's something that the back end does not want to make accessible to the users, they're not going to make it accessible. We're not going to write that in our servers. We're not going to allow them to have access. This is where our security comes from. If we have something that needs to be secure, we're going to keep it on the back end, and we're not going to give the client access to it. So for example, a bank with a database with all kinds of sensitive information and functionality to be able to transfer funds and things like that, none of that is going to be accessible on the front end. We're never going to send that functionality to our users. We're going to keep that on the server and verify absolutely everything. Anything that the user sends us, we're going to verify on our end. because again, they can modify anything that goes over here. The front end cannot be trusted. All security has to happen in the back end. But for now, that terminology, front end and back end, front end, browser, back end, that's all our server-side code that we're writing, that we don't give to the clients, to the users. For HTTP, there are several types of requests. We'll mostly focus on GET and POST. The other ones are sometimes used, but not too often. GET and POST we'll use extensively. So GET, this is an HTTP request where the browser, where the user is saying, give me something. I want to get this content. Give me this content. And POST is where the user is sending content to us, to our server. Here, I want to post this content to you. The POST is mostly used, I have slides on this. GET is used just to get information. Give me index.html, give me style.css, give me your JavaScript files. All this is GET. Give me that image. All those are going to be GET requests. And then the POST request, this is when, say, a user's filling out a form. That's when we're going to have a post. Maybe they're registering an account. Maybe they're logging in. These are going to be POST requests because there's information that the user is sending to us. And the lines sometimes get blurred. For example, a Google search is actually a GET request. They use something called query strings to code that. We'll actually see that in a few slides. So it's not always whenever the user wants to send some information, but this is the typical boundary. And as we'll see when we build these servers, the difference between GET and POST is just the characters GET and POST. And then that's just a signal to the developers of communicating, hey, this is the intent of this request, is mostly, for the most part, the only difference. It's very superficial, just like any protocols, but it's kind of, but this is even more superficial. It's kind of just agreed upon by developers. If this is your intent, especially with put and delete, if this is your intent for this type of request, use this type of request. Put and delete could easily be GET and POST requests, just depending on how the developers want to code that. But put and delete, these are kind of telling other developers what the intent of the request is. So again, no magic here. Sorry to disappoint anybody. There's really no magic with any of this. Once you're done with this course, you'll be like, oh, the internet's not as cool as I had hoped. It's not as magical as we want to believe. So when we make an HTTP request, the first thing we need to worry about is the path. Well, I guess I have all this on one slide, so let's talk about it all. A URL is going to have these parts, a uniform resource location. This is the location of anything, as the name implies it is uniform, and it can also specify resources that are on the internet. So for example, when we just opened our HTML files in the browser from our hard drives, we use the file protocol and then the path of our of that file. Where is that file on our hard drive? So nothing, so this is going to locate any resource and just happens to also be able to be used for resources on the internet. For our purposes, we'll have protocol being HTTP, : / and then later HTTPS, : / the host. This, we usually use a domain name, but this does have to be an IP at some point. That's where our DNS servers are going to kick in. But the host, where is this going? The port, which port number on that host are we communicating with? This we've already seen. I shortcutted this to just host and port when I went to the server, the TCP server that I ran, but my browser just added, it said, you know what, you probably want to use HTTP, so it added the HTTP / : for me. We just don't have to type that these days in our browsers. But that was added. I did HTTP : / localhost, which will resolve to that 127.0.0.1 : 8000, and that sent that HTTP request for just the root path. Then next is the path. This is what specific resource is being asked for. If this is blank, we're just going to get slash just the root path, which is usually where we're going to host index.html or whatever we name our main HTML. But what resource is being asked for? A literal question mark character if we have an optional query string or fragment. An optional question mark if we want to add some more information in the form of key value pairs. We'll get in depth into this next week. We want to add more information, we can use a query string. And then if we have an optional fragment, the hashtag character, and then some extra fragmented information there. So this is the structure of a URL, which we'll use throughout the semester. Yeah, question. So the www, that's part of the name of the server. So the host, you're going to register a domain name, say buffalo.edu. We're going to register that domain name, and then anything in that domain name gets routed to us. It's linked to our IP address. Then we can also add subdomains to that if we want to prefix that with something.buffalo.edu. So if we have CSE.buffalo.edu, that's a subdomain, and then the UB's network, once the internet routes it to our IP address, UB's network is going to route that specific request to the CSE server running on this network. And then www is just a common subdomain that just kind of became a standard. You name your, you'll have different servers on your network. Most of them are internal servers, and whatever one is hosting your website, you just call that www. A lot of companies, a lot of organizations stuck with that convention. So let's see a few examples of this. If I want to send a search request to Google, I'm going to send a GET request to something that looks like this, a URL that looks like this. /search is the specific resource, or the specific path for this resource that's accessing their search engine. And then they use query strings. This is why they don't use, not necessarily why, but this is what they use instead of post requests. Lost my mic. This is what they use instead of post requests is query strings. So they use a GET request, and then what you're actually searching for is going to be a query string, which is followed by a question mark, and then key value pairs separated by equal signs. So there's a key Q, short for query, with the value web development. This is going to perform a search for web development on google.com. If we paste this URL right into our browser, we're going to get the search results for web development, just as if we punched web development into Google search. This is how Google is coding those requests and sending them to their server. If we have multiple key value pairs in a query string, we're going to separate them by an ampersand. If we want these fragments separated by a hashtag, so for example in Wikipedia, if I want just the URI page, I'm going to go to this link. But if I want to go directly to a specific section, if I want to go directly to the definition section, I'm going to use this hashtag definition. It's just how Wikipedia happens to have set up their site. So if you click on, you have the summary at the top of the page. If you click on one of those links to jump to that section, it will actually change your URL up in the address bar. It'll add this fragment to the end. And then if you want to send somebody a link or host a link directly to a specific section in Wikipedia, this is how it's going to that specific section. It's by using these hashtags, hashtag fragment, and then that link is going to take you directly to that section. And we briefly saw an HTTP request in my TCP server, but this is the fundamental structure of a request, which this is a good place to start on Friday because we're going to parse this apart and talk at length about it. So let's stop there. We're at the end of time. So I'll see everybody on Friday.